Hello, everyone. My name is Benjamin Garrett, and I'm the head of new product introduction for specialty gases and delivery systems for Merck Electronics. And I'm excited to talk to you today about molybdenum and the art of gas delivery. We really feel like we have a game changer in deposition processes, and that's focused on our ability to generate high purity materials and have a best-in-class delivery system. So thank you for the opportunity to talk to you today, and thank you for your attention. So we're going to be running through just a moment of gratitude for the times we live in. I think it's an exciting time to be alive, and we're going to drill into why I think that and why I'm excited to be working in the semiconductor industry. Then we're going to go into states of matter, specifically around delivery systems for various states of matter, gas, liquids, and solids. Then we're going to dive into solid sublimation, specifically around containers, different strategies for delivery with solids. Then we're going to go into the chemistry of molybdenum dichloride itself, some really small nuances in the chemistry itself that have a big impact on overall performance of the purity of the precursor and the delivery of the material itself. Then we're going to really drill into our theory of operation on our ChemKeeper vapor product line, our delivery system for molybdenum dichloride, specifically why we're able to go to higher temperatures and why that matters. And then finally, we're going to present on data that verifies our state-of-the-art performance on pressure and flow stability and utilization. So to start, we want to, think about the world we live in today and why are we all working in the industry we're working on. It's I think some of the most exciting, highest technology ever operated, and so I really want to drill into where we're at today and how exciting it is to be working in the semiconductor industry today. So if you think about accessibility of knowledge and information over the last 150 years or longer, starting in the 16 to 1700s, there's a standardization of how science was reported. This is, the kickoff of scientific literature. There was some textbooks and that sort of thing. So some basic standardization of scientific communication kicked off in that time frame. Fast forward to the 1800s, you have the printing press, and so you're able to publish a lot of information via that way, so more accessible information then. This one really was surprising to me. So wide availability of public libraries wasn't until the early 1900s, and so information was really siloed into kind of an elite stratum of society. So public libraries opened up knowledge and information to a wider range of people. TV broadcasting in the 1940s and 50s, so people transitioned from really only getting their information from reading to TV and radio. And then the internet comes along, and that's where things started to speed up as far as accessibility to various pieces of information. And so search engines started in the 1990s and 2000s. Some of us are old enough to remember when you couldn't Google everything. If you wanted to find or research a topic, you went to the library or you went to your encyclopedia, and you read, you flipped through pages and you tried to find the information you needed. And then online search and really online learning really kicked off in 2010 timeframe. During my time in college at the University of Illinois, I was part of a first class that did a online organic chemistry course. It was controversial at the time, but it was really ahead of the times as far as what learning will look like. And it was an online course, open tests, so you had the access to the internet. And surprisingly, the curve was still pretty significant. The scoring curve was still pretty significantly low. So even if you studied, even having open internet didn't help with grades too much. So it really showed that information is key, but having the foundational knowledge to be able to find that is also key. And then fast forward to today. Almost everyone in here, I would imagine everyone in here has used AI to some capacity. If you're like me, you use it for a lot of different things. And if you think about where we're at today, we start with sand, we process that into silicon, we do various semiconductor unit operations on that to build the chip that gets integrated into a device. And somehow along the way, coating on top of that, we turn sand into expert advice. And what I mean by that is AI is expert advice on any topic you can imagine at your fingertips. Just imagine how cool it is. 100 years ago, you had to go to a library, find a book, become an expert by reading through things. Now you're able to access from medical information to deep nitty gritty physics on a topic you're interested in to all sort legal information. So much is at your fingertips right now. It's a really cool time to be alive, and I think it's a privilege to be able to participate in some small way in bringing forth this expert level input to anyone with access to the internet. So this is just a brief moment to appreciate the times we're in. It's a cool time to be alive. Next, we're going to transition into states of matter and the delivery and various strategies of delivery for gas, liquids, and solids. So I'm not an expert in semiconductor processes. Um, I'm an expert in materials and chemistry, and so just to highlight, my high-level understanding of what our customers do. It's the most technologically advanced manufacturing process known to man, and they're doing it day in and day out. Um, but fundamentally, you pattern your silicon, you drill it, you etch it, you fill it, you deposit, and then you polish. So drill, fill, CMP. I got this from a course at SUNY Albany many years ago, and it really stuck with me. It drastically simplifies the overall process, but it really highlights the fundamental flow of how semiconductor chips are made. And so really specifically, etch and deposition, we definitively need a gas in the chamber to do the work. Patterning, there's next generation patterning for EUV, where exploration of a gas delivery deposition process is underway. So fundamentally, a large portion of semiconductor processing in general requires gas to get to the chamber. And so what we're going to be going into next is, gas, state of matter, liquids, and solids. How are different strategies utilized to get to the gases that we need in the deposition chamber? And so, as I mentioned, I'm not a semiconductor process expert, but where my expertise and where Merck's expertise lies is really around the chemistry, packaging, and quality. And so this is a gross simplification of the overall supply chain, but I think it's informative. Our customers are undergoing the most advanced manufacturing processes in the world, period. And they're doing it day in and day out. And so what they need is high quality suppliers that know the importance of that advanced technology, and they fundamentally know how to build in the quality and consistency of supply that makes certain that advanced chip manufacturing isn't compromised at any state. And so a good supply chain partner like Merck really ensures that your job is easy. So materials wise, high purity, high quality, consistency, delivery, state-of-the-art uptime. Those are the things that our customers want. And so there's a mantra, within the supply chain that no news is good news. So when things are operating smoothly, that means we don't hear from the customer because everything's operating exactly how it should be. So no news is good news. And so it's been a real privilege to join the Merck team and get to know the team. The breadth of expertise has been amazing across all sorts of fields, from engineering to chemistry. And so it's been really, really neat for me to see the first principle engineering and then really the deep chemistry expertise and how we bundle all of those together to make the best offering possible. And so we're really going to drill into moly dioxide dichloride and how deep chemistry expertise leads to the best purity out there, and how that ties into our delivery system and why our delivery system is differentiated. So before we drill into details, we'll do a quick fact check. So fun fact check. What's the most abundant state of matter? I'll pause for a second for people to think about it. And the most abundant state of matter in the universe is actually plasma. So stars are plasma. So we're not talking about plasma today, but just a quick fun fact check to make sure we're all engaged. But now we'll move on to really drilling into delivery of different states of matter. So let's start with gas. So in general, the industry really started around gas delivery. It's the state of matter you need in your chambers for deposition and for etch. So getting material from the container to your tool is fundamentally a matter of gas management. So you're not transitioning states from liquid to gas or from solid to gas. You're already in the gas state, and so you need steady supply, steady pressure, steady flow. And so fundamentally, that means a series of various regulators, pressure monitors, to make sure you're going from the fundamental vapor pressure of the chemistry, or sometimes it's heated, to whatever the demanded pressure is at the tool. And so that can be a mechanism of a regulator, for example. And so tungsten hexafluoride is an example that's been delivered for quite some time. And at a high level, the way that goes from a relatively high pressure gas in the 800 to 900 torr range to less than 100 torr in the customer chamber. Fundamentally, how you manage that is a regulator. These are specialty regulators. This is where expertise is flexed within Merck. These specialty regulators, because tungsten hexafluoride is a toxic gas, it's a corrosive gas, so you can't just buy any brass regulator off the shelf. You need a highly specialized piece of equipment with right materials of construction. So even though gas delivery is probably the simplest relative to liquid and solid, there's still a lot of expertise baked in to how to do gas delivery well. But fundamentally, you have your precursor, your pressure generator. So this is where your chemistry pressure is coming from. And then you have, a valve oven and pressure distribution. So pressure generator, distribution of your gases, and then final delivery to the tool. And then pressure management, down regulation as appropriate for various gases along the way. But overall, gas delivery is generally perceived as the simplest delivery option out there. So as we advance down the spectrum of complexity for delivery complexity, we go on to liquids. So we're not delivering a liquid to the deposition chamber for the most part. We need it to get it to a gas. And one of the most fundamental complexities when it comes down to liquid delivery really ties to a large number of precursors have some thermal stability concerns. Not every precursor, but many of them do. And so the ones with that are especially thermally sensitive, that's where complexity increases a fair amount. And so an example of how you manage a sensitive precursor and getting it to the fab floor is you have a large container hookup. So this would be a bulk subfab connection. You distribute liquid to a valve manifold box, and so your valve manifold box then distributes to multiple tools. And then the multiple tools, and this is just a cartoon picture of a ChemGuard. So this is your local bulk. And so basically you're able to, so if your large bulk runs out, you're able to change without any downtime because your local bulk's full. And then you're able to continue fill your local bulk. And then here's an example of a process container, and this is where you get to the vapor pressure you need and delivery to your chamber. And so this local process container increases complexity. Low vapor pressure materials require a bubbler, so you're purging gas through the solution to aid in getting to the pressure within the chamber that you need. So a bubbler is inherently more complex than a basic gas delivery container. So again, we're increasing in complexity. Particularly sensitive materials may need something like a direct liquid injector, or even distribution to a local process container. So you're getting the process container as close to the chamber as you can. And so all of those are various strategies that are leveraged for thermally unstable material, and it increases the complexity significantly from, say, a gas delivery system. And so this is a very basic cartoon of distribution. And then here's a more detailed picture of a bulk delivery system, a VMB, and a ChemGuard or ChemKeeper delivery system, and then your process tool. And so now we're moving on to solids. And so I wouldn't necessarily say solids are drastically more complicated. It kind of depends on the solid. It's at least equivalent as a complication as liquids. Part of the complexity with solid delivery is that it's new. It's new to the semiconductor. It's relatively new to the semiconductor industry. So there's lots of kind of engineering aspects that have to be worked out, such as components that go to higher temperatures. Corrosion, which we're going to touch on quite a bit later on. But there's various components and complexities within the solid. But if we think back to our gas discussion, so we have a pressure generator here in the container. And so in a gas cylinder, the material's gas to start. So there's, sometimes you heat it to get to higher vapor pressures. But for the most part, you start with gas and you're managing the pressure. So for solids, you're obviously not in a gas state. So you have to go from solid to gas. And so that's fundamentally what sublimation is you're going from solid state to a gas state. And so where this is where fundamentally we're getting a shift in complexity, especially for solids. We talked about direct liquid injectors and different distribution methods for liquids. A lot of the complexities within a solid delivery system is fundamentally how you get heat into the solid bed, because you have to get heat into the solid bed. There's a heat of vaporization. You vaporize the material into the gas phase, and you have to keep driving heat in. And so, if an example of a very basic sublimation setup, no infrastructure within a container, this is the pressure engine of your system. This is where all your pressure, vapor pressure of your chemistry is going or coming from to get to your chamber. And so just a really basic example is you have a powder bed of material. You're transferring heat from your sidewalls. Heat's coming from external. So material closest to the walls are going to be driven off first. And constant temperature. So assuming a constant temperature, because you have a lower heat transfer area as you deplete material. So fundamentally, you're going to have a lower pressure, delivery pressure. And so you're changing the dynamics of heat transfer the more you deplete material. So this fundamentally, this basic sublimation demonstration is where delivering solids adds a fair amount of complexity. And so we're going to go into more details in the coming slide on that. So now that we talked about gas, liquids, and solids, we're really going to drill into container design and why different strategies are chosen and pros and cons of different strategies. And so there's only a finite number of ways to design around sublimation. So as we mentioned in the last slide, it's all about getting heat transfer in. So there's various strategies. So starting from a blank sheet, there's various strategies to approach this problem. And fundamentally, what you're trying to get to is a heat flux. And so there's only so many different parameters to tweak to get to your overall material flux. And so you can tweak temperature, you can tweak surface area, or you can tweak your coefficient, your heat transfer coefficient. And so, very basic cartoons of different strategies to do that. So for example, if you want to increase your area, so high surface area, you can do something like a trade system, where that trade system is fundamentally intended to drive heat into the powder bed. And so you're in this scenario, you're driving your area up, your heat transfer area up. There's a lot of complexities in this. The overall container cost is going to go up because it's complicated. You have trade systems. Loading it can be difficult. Cleaning it can be difficult. And you have the fundamental problem where your heat transfer area to powder bed changes as you deplete. We'll talk about that a little bit more in the next slide. A different strategy is really trying to adjust your local temperature. And so you can insert a heater into the container to really drive up that temperature. So as the powder bed drops, your powder is going into here. And so this center cartoon is really around local heat flux control. So you're driving heat into where the powder is going to go. But part of the issue here is, again, your heat transfer area is adjusting as you're depleting the powder bed. And as you deplete the powder bed and your heat transfer area adjusts, your pressure changes, your delivery pressure changes. And so the behavior of your pressure and flow is going to change as you deplete your vessel. And then finally, the last factor to really, address your flux is the coefficient. And so if you have a material where you're able to get into a liquid state, where you're able to melt, then you're changing the coefficient. And so fundamentally, this is through convective heat transfer. So liquid's mobile. So hot liquids will move to areas of lower temperatures. And so you get convective mixing. Even in the absence of a mechanical mixing, you're going to get convective mixing that distributes heat throughout the container. And so this ultimately means you have pretty consistent high interface heat transfer throughout the whole duration of the container. You have reduced thermal gradients because you're liquid and materials moving around, and that heat transfer is good. You're going to have a more constant source pressure. So even as you deplete, because that heat transfer is good, you're going to have good delivery pressure. And then you're really able to utilize almost every molecule within that. So these are various different strategies that you can take when considering delivery of different solids. And so let's drill into varying the area and then the heat transfer. And so this basic cartoon shows full containers, and then as you're depleting containers, to really illustrate this concept here, as you deplete the container, you're changing your heat transfer area. And so as you deplete your container, if you need constant pressure, which our customers do, if you need constant pressure, one strategy to consider to do that is you raise the temperature. So as your heat transfer area goes down because your container levels are going down, or your material levels are going down, one strategy could be is you raise the temperature to maintain that constant pressure. And so this is where we drill into some nuances within the chemistry. So we talked about different delivery strategies for solids, controlling the flux by either controlling surface area, controlling heat inputs, or controlling the coefficient, so changing to a liquid state. And so we're really going to drill into some fundamentals of molybdenedichloride hydrate chemistry and why different solutions will lead to higher purity materials and better delivery. And so we're really going to focus quite heavily on this equation here and walk through different pitfalls of different strategies. So molybdenum dioxydichloride hydrate undergoes three different phases, three different reactions for decomposition. So the first decomposition shown on this top reaction is you're losing a water molecule. So at relatively low temperatures, you're not getting core molecule degradation, but you're getting water driven off. As you go down these reaction paths, as you increase temperature more, you start to degrade the internal molecule and you're kicking off a chloride via an HCl. So the first decomposition, you lose water. The second decomposition, you lose HCl. And then you have to go, and you can see here in this middle reaction, there's still HCl tied up in this molecule. It's, it's integrated into the core molecule itself. And so you really don't start driving off all your HCl. You don't get to this final reaction until you're at higher temperatures. And so a bit of the danger when you're in a sublimation regime is HCl remains. So this reaction happens, but you haven't driven this reaction to completion. And so you have the raw material with HCl tied up into it. And so if we think about the last example of boosting temperature to get more out of your ampule, let's think about the what could happen from that based on this theoretical or based on this fundamental chemistry of molybdenum dichloride hydrate. So when we're above the decomposition temperature, we're not just driving off hydrate anymore. We're decomposing that central hydrate molecule to form HCl. We still have HCl tied up in this. So as we're going to higher temperatures, so if we're increasing temperatures to get to that constant pressure that the customer needs, as you increase that temperature, there is a danger that this reaction's going to happen. So you basically reach a steady state at the beginning. You start to deplete, your pressure drops, and as the pressure drops, you increase temperature. As you increase temperature, you start driving this reaction forward. So you start decomposing this molecule into HCl. And so you have an HCl source if you don't have appropriately dried starting material. And so it's this fundamental understanding of the chemistry of the molybdenum chloride hydrate that I think Merck shines. So our material has state-of-the-art proton content, and so the proton's tied up in the HCl here. So we measure that, and we have best-in-class proton delivery to the tool, so there's no HCl still remaining, and that has to do with our high purity processing that we do internally. We're going to drill into that a little bit more later and why that matters for the overall ecosystem of molybdenum dichloride. So it's a purity play, so our material lacks that HCl. And why does lack of HCl matter a lot when it comes to molybdenum dichloride delivery? We're really going to drill into that next. And so just to summarize, there's only a certain number of strategies you can deploy to go from a solid to a gas state in your delivery in the customer delivery chamber. And so if you have hydrate around, all of these can be problematic. And fundamentally, if you're not driving to higher temperatures, hydrate's a risk. And so really what we just talked about is sublimation strategies where you're tweaking the surface area or the temperature input, and then the other option available is tweaking the coefficient. But what I was trying to highlight through the deep dive in the hydrate chemistry is, HCl is lurking. If you're not careful, HCl is lurking in your material. And so we need to keep all of this in mind. We need to keep this fundamental hydrate chemistry in mind when we're considering fundamental theory of operations of various systems. And so, but what is really, really key is the purity of the material. So, so the next few slides, what we're going to try to do is convince you why the purity of material matters so much, and show some data reinforcing why material purity matters so much. So the first thing to consider when you're delivering a material, we touched on this in liquids. A lot of liquids have issues with thermal stability. And so that means you can't go to hotter temperatures. You have to be very conservative in your temperature set point because you'll decompose the material. So is that an issue for moly dichloride? And so there's lots of various data you can present on this, but two key points is we've taken DSC data from room temperature up to 250 degrees. No signs of decomposition. So this is a relatively short snapshot showing at relatively short time durations. There's no significant concern of decomposition. If there was decomposition, you'd start to see exothermic reactions happening in this green line here. And then furthermore, we've heated material for 200 degrees for long periods of time, 12 months and longer. And then we take TGA before and after. And so basically the change in residue, there's no change in residue after 12 months of heating at high temperatures. So both of these collectively show that the molecule itself, the fundamental molecule itself, moly dichloride, is thermally stable. And so what's the risk of going hotter to get to from the start point to get to higher pressures, higher flows, and stable pressures throughout? That's where we really want to focus a bit on corrosion. And so corrosion chemistry is quite complex. It's a really interesting, area of research and surface science. But let's start with a really basic example and a very basic question. Will iron rust in the complete absence of water? So in order to get rust to go from iron to iron oxide, will it proceed in the complete absence of water? And fundamentally, if all you were to do is look at this equation, you might say yes. But that's where the nitty-gritty details of the surface science and what's actually happening matters a lot. So fundamentally, iron does not rust in the absence of water. You need water, and water fundamentally acts as a facilitator. So it's an electron highway to be able to get electrons from your iron to your oxidizer, your oxygen. It also aids in pitting. So once you get that oxide layer, it degrades that oxide layer. So there's lots of small mechanisms that that drive. You have to have moisture present in order to rust. So why does that matter for us? So if you think about the rust and water example, let's take that to moly dichloride and Hastelloy base as an example. So instead of iron, we have a nickel, source. That's the reducing agent. Instead of oxygen, we have, a molybdenum 6 oxidation state. And so does this reaction proceed in the absence of a facilitator? So in this case, that facilitator is very likely going to be HCl. Any moisture around at these elevated temperatures is going to be in the HCl state. It'll react with moly dichloride. So just like iron will not rust in the absence of water, the theory is Hastelloy will not corrode in the absence of HCl. You need that HCl to act as a facilitator to drive the oxidation, to act as that electron highway. So in the absence of HCl, moly dichloride and nickel alloys perform well. You need to go to extreme high temperatures to drive a direct reaction here. And so what data do we have to support this? And so we have a mountain of different compatibility studies, but I think the most compelling evidence we have is our equipment internally that we've operated for long periods of time. So what you're seeing here is a VCR gland that's been under operation of high temperature moly dichloride, 200 degrees C for long periods of time, 6 months. And we've confirmed via separate analysis that the HCl of this material is low. And this gland is spotless. After 6 months of operation, this gland is spotless. In a separate scenario, we were troubleshooting our system and material wasn't in spec for protons. we saw leaks. And so when we open up the HCl gland on a system that we know we have HCl, we know we have leaks, you get this blue residue. So this is an example of, in the absence of HCl, no corrosion. In the presence of HCl, corrosion. It's just like the water and rust example. So in the presence of that facilitator, you're driving that up. And so that's really, Merck fundamentally understands this hydrate chemistry. We fundamentally understand within our processing of how to remove this HCl. And so our material is state-of-the-art HCl content, highest purity HCl. And so that means we can drive to higher temperatures in our delivery system and not get corrosion. So that's going to be a really big deal for pressure stability, flow stability, and utilization, which we're going to drive into next. All right. Now we're going to really go into, briefly go into the theory of operation for our delivery system. So quick recap, we went through gas delivery, liquid delivery, solid delivery. We talked about different strategies to sublime. It's really about driving heat into the powder bed, changing those, you can change the coefficient, the area, or the temperature. So in general, you need to increase the ampule temperature as you deplete in a sublimation scenario. So as you increase that sublimation temperature, you're at risk of driving that hydrate reaction forward. You still have HCl pent up because you're not hot enough, and having HCl pent up means you're driving that reaction forward towards HCl. And so really where Merck's offering shines the most is our HCl. Our HCl content is state of the art. And why does that matter in the whole ecosystem? Why does that matter for delivery of moly? And that's, we're going to spend the final few slides talking about that. But Merck approached the delivery of moly, with this chemistry input, but also with fundamental, what is the most practical, best solution for our customers in long-term delivery of moly dioxide. So we're going to show stable flow and pressures, 100% utilization of the ampule, stable quality throughout delivery, and you are able to maximize fill weights due to the simplicity of our system. So really quick, fundamental theory of operation for our system. So again, we have our pressure source. You're driving heat into that. So we're at pressures of greater than 2,000 torr. So we have plenty of upstream pressure for pressure stability. We control that pressure in our valve box. And so we have high upstream pressure. We're managing that pressure to get a rock steady pressure. So we're down regulating to a rock steady pressure and flow for our customers. And then we have 4 sticks available today. So one of the advantages of this HVM ready solution is we're fundamentally treating moly dioxide dichloride as a gas. We're going to hotter temperatures. That means we're higher upstream pressures. So this system operates almost like a gas delivery system. So all the simplicity we liked of a gas delivery system is kind of baked in to the moly dioxide dichloride delivery system. So our moly dioxide dichloride is a thermally stable molecule. Our material is HCl free. So that all of that means we can go to higher temperatures, better upstream pressures, better stability, better flow. So let's go look at what the flow variation and the pressure stability and utilization looks like in the last couple of slides. So this is an example of flow through multiple outlets, multiple sticks. So we're able to go to 1 chamber, 2 chambers, 3 chambers, back down to 3 chambers without any major disruption in pressure stability or flow stability. Again, we've shown this multiple times. Our system, because we have such high, we have that high upstream pressure, higher flow doesn't impact our system. We have plenty, our engine has plenty of pressure to supply pressure and flow. So as the industry goes to higher pressures, higher flows, our system's ready to handle that today without any changes. And this is really utilization. So because we're at higher temperature operation, because the fundamental different theory of operation of our material, we're able to get to greater than 99% utilization. We're using almost every molecule of molybdenedichloride in there. We're not leaving, 5, 10, 20% on the table. We're not having to change conditions as we deplete the container. It's a set condition, high pressure upstream, and a stable flow, stable delivery throughout the lifetime. So we've demonstrated greater than 99% utilization multiple times now. We also have auto switchover. We switch over at -2 psig, or a little over 600 torr. So we're switching over at the pressures that we're switching over at is relatively high. So our upstream pressure, there's plenty of pressure supply from our whole system. And then finally, due to the whole ecosystem we're leveraging, the higher temperature operation, the more simple container, we have a 70 kg offering today. Right now, 70 kgs are available today, and 100 kgs are available as well. So it's the next generation offering, but it's minimal tweaks to our delivery system, and 100 kgs are available as well. All of this is tied to that ecosystem, our deep understanding of chemistry, high purity material, and our fundamental theory of operation. It allows us to go to higher fill weights relatively easily. So we'll conclude the talk with just an overview of key advantages of the whole Moly-Merck ecosystem. The first principles designed from both an engineering and a chemistry standpoint, all of those factors play in together, and we're leveraging the best solution from a first principles approach in utilization, stable pressure, and flow. So we're not changing conditions as we deplete our container. The conditions are set, and we're utilizing nearly every molecule in that container. The high purity material really enables a fundamental different theory of operation for our delivery system. High purity means we go to higher temperatures, means plenty of supply pressure for current processes, but even future demand where higher pressures and higher flows are needed. Because we have such a solid grasp on the fundamentals of this material and the fundamentals of this delivery, our overall solution is reduced in complexity, which means reduced cost of ownership, and it enables reliable multiple chamber operation today. We're ready for multiple chamber operations today. Again, high utilization, tight pressure control, that's demonstrated soundly. This fundamental shift in how we operate, because our material purity is so high with regard to hydrate and HCl, that enables us to operate in a different world, where higher operation temperatures means better pressure stability, better flow stability, better utilization. And so overall, we have a scalable, cost-efficient delivery that's aligned with manufacturing and uptime goals. Thank you so much for your time. We'll watch a brief video highlighting the Merck solution for molybdenedichloride.
인공지능과 고성능 컴퓨팅의 발전은 강력하면서도 에너지 효율적인 칩 설계를 요구합니다. 업계의 새로운 게임 체인저로 떠오른 금속 몰리브덴은 고집적 구조에서 높은 전도성과 낮은 저항성을 갖고 있어 불이나 텅스텐 같은 기존 소재들을 능가합니다. 몰리브덴은 칩 제조사들이 더 작은 노드 크기로 전환하고 더 복잡한 칩 아키텍처를 채택하며 에너지 소비를 줄일 수 있도록 돕습니다. 몰리브덴을 반도체 제조에 사용하려면 과학적 정밀성과 첨단 엔지니어링이 모두 필요합니다. 이 금속은 첨단 증착 공정을 사용하여 칩 위에 나노미터 규모의 극방막으로 증착됩니다. 첫 번째 용도는 3D 낸드 메모리 칩의 워드 라인층에서 사용될 것입니다. 이러한 공정들은 몰리브덴 디클로라이드 디옥사이드와 같은 특수 전구체를 필요로 합니다. 융점이 175도씨인 이 반응성 분자는 수분에 매우 민감하기에 정밀한 온도 제어가 필요합니다. 화학 분야에서의 우수성과 원료부터 최종 제품까지 통합할 수 있는 능력을 통해 머크는 최고 순도와 품질 기준을 충족하는 초저수분 몰리브덴 디클로라이드 디옥사이드를 생산할 수 있습니다. 머크의 맞춤형 솔루션인 고품질의 몰리브덴 디클로라이드 디옥사이드와 첨단 공급 시스템인 캠키퍼 시리즈를 결합한 것으로 처음부터 대량 생산에 최적화되도록 설계되었습니다. 이 시리즈들은 정교한 압력 제어와 함께 높은 유량을 안정적으로 제공하여 최대 가동 시간과 신뢰성을 가능하게 합니다. 또한 최고 수준의 고밀도 용기 충전 기술과 99% 이상에 달하는 최적화된 소재 활용도는 고객사에게 가장 낮은 총 소유 비용을 제공합니다. 캠키퍼 공급 장치는 화합물을 가스로 변환하여 공정 장비로 전달합니다. 정교한 공정에는 온도와 압력을 정밀하게 제어하는 기술력이 필요합니다. 머크의 첨단 공급 시스템은 완벽한 정밀함을 구현하며 소재 용기 전환 시에도 공급 중단 없이 소재의 안정된 공급이 가능합니다. 소재 생산에서의 독보적인 품질, 업계 최고 수준의 용기 충전 기술, 99% 이상의 소재 활용률, 그리고 수십 년에 걸쳐 축적한 캠키퍼 시스템의 노하우, 이것이 바로 머크의 대량 생산 최적화가 적용된 몰리브덴 솔루션의 진정한 강점입니다. 머크의 몰리브덴은 반도체 제조사의 가장 중요한 안정적인 대량 생산과 최저 총소유 비용을 동시에 제공합니다.
All right, thank you for everyone's time.